Today we will be doing kinetic theory of gases. In kinetic theory of gases, there are first of all 6 postulates of kinetic theory. The first postulate says that all gases are made up of molecules moving randomly in all directions. So according to the first postulates of kinetic theory, the molecules of a gas are moving randomly in all possible directions. Secondly, the size of a molecule is much smaller than the separation between the molecules. So, according to the second postulate, the size of a molecule is much smaller compared to the separation between the molecules. Thirdly, the molecules will not exert any force on each other except during collision. Fourth point, all the collisions of the molecules are elastic and time of collision is negligible. So in the these are the first 4 kinetic theory postulates. All gases have molecules which are moving randomly. The size of molecule is much smaller than the separation between molecules. There is no force between the molecules except the force during collision, and all collisions are elastic and the time of collision is negligible. Number 5, the gas molecules obey the laws of Newton. Number 6, Number 6, the density and distribution of molecules with different velocities is independent of position, direction and time. Now what does this 6th point mean? What is the meaning of the 6 point? Let's discuss that. Suppose there is a region where the gas molecules are present. Now in this region, suppose inside this region, suppose we select a 1 centimeter cube where there are 2 into 10 to the power 19 molecules. I repeat, suppose there is a cubical region and inside this there is a 1 cc volume which contains 2 into 10 to the power 19 molecules. Now according to the sixth postulate, this quantity is the same for any 1 cc anywhere inside this volume, and this quantity will not change with time. So as time passes by, in any 1 cc you will get this many molecules. Secondly, suppose let us say that in a particular 1 cc there are 400 molecules with velocity parallel to x-axis. Let us say that there is a 1 cc somewhere where there are 400 molecules with velocity parallel to x-axis. So that means that this number will not change with time. And another thing is that if there are 400 molecules with velocity parallel to the x-axis, then there will also be 400 molecules with velocity parallel to y-axis, and so on. So this is what the sixth postulate means. Now we will derive the gas laws with the help of these postulates. Suppose there is a cubical container, and in this cubical container this is the x-axis, this is the y-axis, this is the z-axis. So there is a molecule whose velocity components, are Vx, Vy and Vz. At a certain time, this molecule is found to approach the front face, that is this face. Now let us say the area of the face is A. So if the area of the face is A, when the molecule collides with this face, after the collision, because the collision is elastic, the molecule will rebound with the same component Vx. So the change in momentum will be minus mvx minus mvx. So that is equal to minus 2 mvx. So this is the change in momentum of the molecule after it collides with the front face. Now because it is elastic collision, and by the way, in any collision momentum is conserved, so we can say that change in momentum of the wall will be plus 2 mvx. right? So change in momentum of the molecule is minus 2 mvx and change in momentum of the wall will be plus 2 mvx. Now this molecule will travel to the opposite wall, the wall which is opposite to the front face, that means the back face, and then it will collide and return and again come back and collide with the front wall. So we can say that number of collisions in unit time, this will be equal to 1 by 2L by Vx. Now the thing is, we are assuming that the dimension of this cube is L. So between one collision with the front face and the next collision, the total distance is 2L. So number of collisions per unit time is 1 by 2L by Vx. So this becomes Vx divided by 2L. So number of collisions per unit time is Vx divided by 2L. Now, in each collision, the momentum transferred to the wall is this. In each collision, the momentum transferred to the wall is this. Therefore, momentum transferred per unit time mvx square by L. So momentum transferred per unit time is mvx square by L. Now the total force is m by L into summation Vx square. Now, thanks to the sixth postulate, summation Vx square, summation Vy square, summation Vz square, all are equal to each other. So that is, each of them is 1/3 summation Vx square plus Vy square plus Vz square. So that is 1/3 of summation V square. Now you know that momentum transferred per unit time is this. So total force is this. That means we can now say that the total force is equal to m by 3L summation V square. So this total force, if the mass of each molecule is small m, then we can also write the total force like this. But since we are discussing gases, what really matters is the pressure. So the pressure will be 1/3 mn by L cube into summation V square by N. So Mn is the total mass. So let the total mass be capital M. So this is the important equation. 1/3 capital M into summation V square by N. So this is the equation, the primary equation which will help us to derive all the gas laws. So this is the most important equation of all, that pressure due to the gas is 1/3 mass by volume into summation velocity square by N. Now summation velocity square by N, if you take the square root, summation velocity square by N, if you take the square root, that is known as root mean square velocity. So why is it called root mean square velocity? Because you are first squaring the velocity of all the molecules, then you are taking the mean of those squares, and then you are doing root. So this is called root mean square velocity of the molecule, summation V square by N. Now using this we can say that the pressure is 1/3 M by V into Vrms square. So in order to find Vrms, we can use the formula 3 into pressure by density. So Vrms is root over 3 into pressure by density. Now the thing is that what is the kinetic energy of each molecule? It is half into small m into V square. This is the kinetic energy of each molecules. So the total kinetic energy will be the summation of this . So we can write half small m into capital N into summation V square by N. Now small m into capital N, we can write it as the total mass. So this is the total kinetic energy. So the kinetic energy per molecule will be equal to half m Vrms square. So this is a very important result. The average kinetic energy per molecule is half m into Vrms square. Now during this period of time when the kinetic theory was being evolved, there was a parallel discussion that the scales of temperature which were known at that point of time, the Celsius and Fahrenheit scale, they were dependent on the physical properties of some material. For example, we depend on the expansion of mercury or the resistance of a uniform wire. So it was decided that there should be a universal scale of temperature, an absolute scale, which does not depend on the physical properties of any one particular substance. So that scale was known as the Kelvin scale. Now in the Kelvin scale, it was decided that suppose if you use this formula, P is equal to 1/3 suppose in this formula the pressure is 1/3 of mass by volume into Vrms square, and let us take a particular temperature like triple point of water. So the pressure at triple point will be 1/3 mass by volume into V triple point square. So if you divide these two equations, then pressure by triple point pressure is Vrms square by V triple point square. Now the Kelvin scale was designed in such a way that the ratio of pressure is the same as the ratio of temperature. So pressure divided by pressure at triple point equal to temperature divided by 273.16. So from this we are getting T is equal to 273 by 16 by VTR square into V square. So this is a formula by which we can directly calculate the Kelvin temperature. Now the thing is that we already know that the average kinetic energy per molecule depends on Vrms, and now you can see that the temperature is also proportional to Vrms. So this means that the temperature is Kelvin temperature is proportional to the kinetic energy of the gas molecules. Already you have seen that the average kinetic energy per gas molecule is proportional to Vrms square, and just now we found that the temperature is also proportional to Vrms square. That means the average kinetic energy and Kelvin temperature are proportional to each other. What this means is that you can take samples of different gases, but half m Vrms square, that is average kinetic energy per molecule, will be the same for all the gases. So this value will be the same for all the gases. Now PV is 1/3 into capital M into Vrms square. So we can say that if temperature is constant, then PV is also constant. Because just now we had discussed that if the temperature is constant, just now we had discussed that temperature is proportional to Vrms square. So if temperature is constant, PV is constant. That means P is inversely proportional to V. This is called Boyle's law. Secondly, suppose pressure is constant, then volume is proportional to Vrms square. That means volume is proportional to temperature. This is called Charles' law. If volume is constant, then pressure is proportional to Vrms square. That means pressure is proportional to temperature. This is called Gay-Lussac's law. So these are the three very, very well-known laws: Boyle's law, Charles' law, and Gay-Lussac's law, and you can see that all of them are derived from this primary equation. Now, we know that for any gas, we know that PV can be written as 1/3 into mass of each molecule into number of molecules into Vrms square. So PV is for another gas sample, PV will be 1/3 mass of each molecule into number of molecule into Vrms square. So N1 M1 V1 square is N2 N2 V2 square. So you have two different gases having the same pressure and having the same volume, and if the temperature is same, then this expression and this expression will be the same because this is proportional to the kinetic energy. So these two will be same if temperature is same. That means N1 equal to N2. So this is the very well known Avogadro's law, that at identical conditions of pressure and temperature, equal volumes of all gases will have the same number of molecules. Suppose you have a mixture of two gases which don't react with each other, and you allow both of them to diffuse into each other, then we can say that the rate of diffusion is proportional to the RMS speed. So R1 by R2 will be V1 by V2. In the meantime, we know that RMS speed, the formula is root over 3 into pressure by rho. So that means V1 by V2 is root over 3 into pressure by rho 1 by root over 3 into pressure by rho 2. So V1 by V2 is root over rho 2 by rho 1. So we can say that R1 by R2 is root over rho 2 by rho 1. So this is known as Graham's law, that if you take gases, two different gases at the same pressure and temperature, and allow them to diffuse into each other, then the rate of diffusion is inversely proportional to the square root of density. This is Graham's law of diffusion. Now, suppose you have a container in which there are different gases. The number of molecules are N1, N2, N3, etc. Now, the force on the walls will be due to each of these gases. So, it will be F1, F2, F3 and so on. So, if you divide force by area, so the pressure on the wall will be P1 plus P2 plus P3, etc. That means that the pressure on the wall of the container will be the sum of the pressure exerted by each of the components. So this is known as Dalton's law of partial pressure. Now, why is it called partial pressure? Because when we consider each of these pressures P1, P2, P3, we are considering the volume of the entire container. So when we take any one particular gas molecule, the volume considered is the total volume of the container. So considering the total volume of the container for each gas, the pressure on the wall is P1, P2, P3 respectively. So total pressure is equal to P1 plus P2 plus P3 and so on. This is known as Dalton's law of partial pressure. PV equal to 1/3 Mn into V square. So we know that Kelvin temperature is 273.16 into Vrms square by Vrms at triple point square. So what we can do is we can make a change over here. We can say PV is N into one-third M VTR square by 273.16 into capital T. So you will appreciate that for a particular gas, this entire thing is a constant. So this constant is known as Boltzmann constant. So PV is equal to NKT, and the value of Boltzmann constant is this. 1.38 into 10 to the power minus 23 joules per Kelvin. Now, instead of saying number of molecules, we can say number of moles into Avogadro's number. So this is Avogadro's number into Boltzmann constant. So PV is equal to nRT. So R is 8.314 joules per Kelvin mole. This is known as the ideal gas equation. Now our primary equation in today's class was this: PV equal to 1/3 Mn Vrms square, and few minutes back we got the Boltzmann equation. PV equal to Boltzmann constant into N into T. If you divide these two equations, one-third M Vrms square is equal to KT. So Vrms is root over 3 KT by M. So if you multiply above and below with Avogadro's number, so you will get root over 3 RT by molar mass. So this is the formula to find Vrms, root over 3 RT by molar mass. Now there are two more formulas. Average speed of gas molecules is equal to root over 8 RT by pi into molar mass, and probable speed is root over 2 RT by molar mass. Probable speed is root over 2 RT by molar mass. Now what is probable speed? Probable speed is the speed of the it is the speed of the highest fraction of molecules having a particular kinetic energy. So according to Maxwell, when you consider kinetic energies of all the molecules, there is a particular kinetic energy which is attained by maximum percentage of molecules, and corresponding to that the speed is root over 2RT by molar mass. So that completes the discussion on kinetic theory of gases.